Now, next session is a special lecture by Professor Mitsuo NOTOMI, School of Science and Technology, titled Shape Memory Alloy, How to Use this Material in Hayabusa Mission. Sounds very interesting, isn't it? Please remember that you can ask questions in the Q&A box, and it will be answered later in the Q&A session. Professor Notomi, please.
Hello. Hello, my name is Mitsuo Notomi. I'm one of professor of this university and belong to the School of Science and Technology. Usually, I teach to my undergraduate students about mechanics of materials, fracture mechanics, metallurgy, and doing some research with my graduate students. But for example, developing the hydrogen absorption material and biomaterials corrosion and investigating the spring microstructure. So I'd like to show you my presentation slides. Please wait a moment. So today, I'm glad to getting a chance to present to you one of my research topics and related topics. The title of this lecture is Shape Memory Alloy and how to use this material in Hayabusa mission. Let's start. The content of this presentation as follows. Part 1. I'll show you some videos or shape memory experiments with some metals and shape memory alloys. And then I explain about the mechanism of shape memory effect and the comprehensive list of binary alloys holding the effect by myself. Third, part 3. I show you the application of the shape memory alloy and how to use this shape memory alloy in Hayabusa mission. Part 1. Shape recovery experiments with some metals and shape memory alloy. Please look at the spring. Please look at the spring. The spring might be made of a certain metal. We apply some force at the end of the spring. Then the spring extends like this. After we release the force, it recovers original shape. We call this behavior as elasticity. If the spring subject more force beyond the elastic, it could not recover after releasing the force, after releasing the force. We call this behavior as plasticity. So you can see that residual elongation is defined as amount of difference between the original length and the length due to plastic deformation. The important point is that normal metal cannot recover the original shape once after occurring plastic deformation. However, a certain alloy consists of 2 or more elements shows shape recovery by heating even after plastic deformation. I'd like to show you the shape memory effect in the way of spring deformation. Before that, please look at the photo. There are the springs using this experiment. The most left side spring is made of iron with high degree of purity, 99%. Second one is made of copper that has the same purity. Third one is a nickel. Fourth one is titanium. Both has the same purity. The most right side spring It's made of titanium and nickel. Its composition is 50 and 50. The diameter of all the springs is about 10 millimeters. That means the dimension is similar to a thumb of your hand. We'd like to see the elements, the specimen, in the periodic table. This is the periodic table. Iron is here. Copper is here. Titanium is here. Nickel is here. All elements are classified as transition metal, and the metal shows plastic deformation beyond the elastic one. Please look at the combination of titanium and nickel. I provide titanium nickel alloy for the experiment as representative of shape memory alloy. The procedure of the experiment is as follows. First, I make a spring from wires. This process is supported by Meiji University's workshop. Second, I expand it until plastic deformation beyond the elastic. And I dipped it in hot water about 80 degrees Celsius. And I check it do the shape recovery or not. The first specimen is a spring made of iron. I expand it until plastic deformation. You can see the residual elongation. I dip it in the hot water. It does not show shape recovery. The second specimen is a spring made of copper. I expand it until plastic deformation. You can see the residual elongation. I dip it in the hot water. And you can see no shape recovery. The third specimen is a spring made of titanium. I expand it until plastic deformation. You can see the residual elongation. I dip it in the hot water too. And it does not show shape recovery of it too. The fourth specimen is a spring made of nickel. I expand it until plastic deformation, like this. And you can see the residual elongation again. I dip it in the hot water. Never shape recovery. The fifth specimen is a spring made of titanium nickel alloy. I expand it until plastic deformation again. You can see the residual elongation again. I dip it in the hot water and then you can see the shape recovery of it. Once again. You can see the shape recovery like this. Okay. This wire remembers a spring shape. Next, I show you the extra specimen is a spring made of the same alloy, titanium nickel layer, but this is struggling like this. Once again, this spring is struggling. Because this wire remembers straight line shape, so that it struggles like this in hot water. We can make the shape memory alloy wire to any shape and record it, the shape, using heat treatment. Okay, I show you the summary of the part one. Iron, copper, titanium, and nickel do not show shape memory effect. Titanium nickel alloy shows shape memory effect. Move on to the part two. I explain about the mechanism of the shape memory effect on the comprehensive list of binary alloys holding the effect making by myself. All metals deform elastic deformation in applying force and recover if one release it the force. If metal deform plastic beyond the elastic, they do not recover although one release it the force. But some special alloy with plastic deformation recover the original shape by heating. This behavior is called shape memory effect, and the materials are called as shape memory alloy. This springs in the photo is made of titanium and nickel. It shows a perfectly recover to the original shape, that is shape memory effect. This effect is closely related to the crystal and the lattice structure of austenite phase, the high temperature phase, and Mauthausen phase, low temperature phase. This slide expresses the atom movement of a crystal for plastic deformation. This figure in upper side shows a deformation behavior of the atoms during plastic deformation in certain metal. This sphere represents an atom, and this bar represents the bond of adjacent atom. Some force is applied at the top of the crystal. So, for moving the atom to this direction, beyond the elastic deformation, plastic deformation has occurred. Plastic deformation has occurred so that the atoms in upper side, the crystal slip until cutting the original shape and making the new bond. This movement is called as slip, and the plane on the slip is called as slip plane. More force applied, then more slip occur. The result of this slip creates a permanent displacement, like this. This lower figure shows the plastic-like deformation in shape memory alloy. The crystal consists of two kinds of elements. We apply the shear force, then atom move like this. More force to same direction. However, the atoms do not move more along the line of the former movement. Instead of this, the slip plane shifts from here to here. And the atoms on the plane move along the same direction, like this. We call this type of movement as twin, and this place of plane is invariant plane. The result of this twin creates a plastic-like displacement, but it disappears after heating the crystal and back to the origin. Because this type of deformation never cuts the initial bond between adjacent atoms, so that the structure holds the relationship between the neighbor atoms even after large deformation occurs. This slide shows the outline of the mechanism in shape memory effect. Please look at the upper side of here. This schematically shows the crystal structure of shape memory alloy in higher temperature. The state is called as alternate phase. We cool it beyond transition temperature, and then the crystal has occurs martensite transformation. And the crystal structure has changed like this, but the outline of the crystal does not change. This temperature is the martensite transition temperature. And this state and the lower temperature is called as martensite phase. We apply some load to it for occurring the plastic-like deformation. In this case, although the outer shape has changed like this, the crystal phase has not changed. We heat it up to the transition temperature so that the crystal transition transforms from martensite phase to austenite phase. As a result, it comes back to the original shape. That is shape recovery. This figure shows the unit cell of titanium nickel shape memory alloy in austenite phase. The structure is named as B2 by structure-Billerith designation, and is one kind of body-centered cubic-like structure in binary elements. The lower one is martensite phase, and the structure named as B19. This lattice is orthorhombic. You'd find it has less symmetry than upper one. This is the high symmetry, but less symmetry. This less symmetry with binary alloys cause that twin deformation occurs. So there are many kinds of shape memory alloy have already been developed so far. I'm interested in how many kinds of shape memory alloy, especially in binary alloy. I focus only on the alloy consists of two elements, shape memory binary alloy. For example, titanium nickel, silver cadmium, but I do not consider about the iron aluminum nickel because it consists of three kinds of elements. I've reviewed more than 100 papers related to shape memory binary alloy and made a comprehensive list of shape memory binary alloy. I show you the list. This is a comprehensive list for 33 kinds of shape memory binary alloy. Already human being has been developed. Area number 1. Crystal system and structure-Billerith designation in austenite and martensite. So these blue area shows the crystal system and the crystal lattice structure in austenite phase. I can classify shape memory binary alloy into three types: B2 type, A2 type, and A1 type, according to the crystal lattice structure in austenite phase. Please look at these figures. They show the crystal system of each unit cell. B2 means a body-centered cubic structure in binary alloy, and each element ratio is about 50-50 with ordered lattice. A2 is similar to B2, but element ratio is not 50 and 50. And so that this has disordered lattice. A1 is similar to face-centered cubic-like structure in binary alloys, and this is also disordered lattice like A2 type. Or the crystal system is cubic. This is important. So that they have high symmetry crystal structure in austenite phase. This area shows the crystal system and crystal lattice structure in martensite phase. The crystal system are tetragonal, orthorhombic, monoclinic, polygonal, and hexagonal. But you can see that there are no cubic. That means the symmetry of martensite is less than austenite. Please look at these figures. They show the crystal system of each unit cell. This is B19 structure. You can see it is a little complicated structure compared with the B2 already I show you in austenite phase. Anyway, B19 is a similar structure of titanium nickel alloy. That is the material of the spring I show you in that movie of the experiment. Please look at the A1 type. The alloy in A1 type transform from very high symmetry cubic to the A3 or A6, they're both not cubic. These crystal system, no, A3 and A6 and also B19 are not cubic. This means the symmetry of martensite phase is less than that of austenite phase. The type of difference in symmetry is one of the reasons for shape memory effect. Second area here, second area shows the element pair and the typical composition of each shape memory binary alloy. Third area shows the percentage of maximum shape recovery and martensite starting temperature and other properties. Please look at this column. This column is a martensite transformation temperature. For example, here is 55 unit is Kelvin, so the 55 Kelvin martensite start. And this is more than 1,000. So this property expands the ability for application of a shape memory alloy. So we can select which temperature is the shape recovery starts. This comprehensive shape memory binary list has to be useful for reconsidering the shape memory effect mechanism and developing a new shape memory alloy. Okay, I show you the summary of part 2. There are the 33 kinds of shape memory binary alloy are classified into B2, A2, and A1 types according to the crystal structure in austenite phase. All of the crystal structure of austenite phase, higher temperature phase, are higher symmetry than those of martensite phase, lower temperature phase. Okay, let's move on to the part 3. I show you the application of the shape memory alloy, how to use this shape memory alloy in Hayabusa mission. But first of all, please take care. I'm not a member of Hayabusa mission and not a researcher of astronomy. JAXA only allowed me to use some photos and figures in their website of the mission in this presentation. Hayabusa is a space probe which returned to the Earth. Among the Japanese space probe, Hayabusa was the first to capture surface samples in all over the world from an asteroid, Itokawa, that is one of Apollo's asteroids. It was launched 9th May 2003. It arrived at Itokawa on September 2005 and operated the sample collection mission on November 2005. At that time, the sampler of Hayabusa touched the surface of Itokawa like in this figure. You cannot see the bullet, but a bullet is launched from Hayabusa to the surface, and the sand on Itokawa is scattered. The aggregated sand, including the fine particles on Itokawa's surface, is an important sample of this mission. The sample travels upward in the sampler like this. Now, the sample is the top of the sample here. This figure shows a sample collection device and the Earth return capsule. The top of the sampler connects this device at here. This device consists of tube set backer, wire cutter, transporter, latch and seal mechanism, thermocaps, and so on. Please look at the sample. This sample moves upward to the center of the device and stay. あ、持った方がいいですか？あ、これでいいですか？ I'm sorry. This device connects to the, Please look at this sample. Now, the sample stays in the device until the next operation. This device connects the Earth return capsule at here. Only the capsule could return, only the capsule could return to the Earth, and any other part of Hayabusa never come back to the sample, never come back to the Earth. So we need to, this sample move from here to here. And then we have to tightly close the lid of the capsule for transporting the sample safely at the entering the Earth's atmosphere. This is the Earth return capsule. Now the sample stays here. In the lid of the capsule, but the lid stay in the device, not the capsule. So that we have to push the lid with the sample from the device to the capsule. So we start the operation, but pull down the sample, and then to push here. So the sample is now in the capsule. It's okay. This figure shows the magnified of the capsule. Hayabusa activates SMA actuator by heating for releasing the latch using the electric power in the battery of Hayabusa. Then the SMA shape memory alloy spring, expands for sealing the room of the lid. The lid closure operation finish completely like this. June 13, 2010, only the capsule returned to the Earth and landed in Australia. This photo shows the capsule with the lid had just landed on the ground in Australia. You can see the lid closed tightly and perfectly. So, a history from the launch to the sample cup closure operation. It was launched 9th May 2003. It arrived at Hayabusa arrived at Itokawa on September 2005 and operated the sample collection mission on November. Before back to Earth, Hayabusa had moved the sample from the device to capsule. The lid closure operation of the return capsule had been operated using shape memory actuator January 2007. The operation by shape memory alloy had done once after about 4 years from the launch in space. Okay, summary of part 3. The lid closure operation is latching the lid and sealing it from outside. The time from launching the rocket to closing the lid is 4 years. The actuator of the operation never done during the 4 years. Hayabusa could be used limited power supply system. That is only lithium-ion battery is available for driving an actuator. And it had to never mistakes, so that the operation had to have very high reliability. Shape memory actuator do not have motor and or engine, so that it was very simple and then very durable, even though under cryogenic environment like in space. It is a big advantage that just tuning on using limited electric power can activate shape memory actuator. using the shape memory alloy actuator for the operation is one of the reasons why this mission has succeeded. If you are interested in the story, please come to Japan and enter not only Meiji University, but also any other Japanese university. Thank you very much for your attention.